What is metal injection molding, MEM? Metal injection molding, MEM, is a metalworking process that combines the injection molding of plastic with the powder metallurgy process to produce complex, precision metal parts in high volumes. It involves mixing fine metal powders with a binder, shaping the mixture, and then removing the binder and sintering the metal to form a final part. Key steps in the MEM process. Compounding: fine metal powders, typically less than 20 micrometers, are mixed with a binder, usually thermoplastics, waxes, or other materials, to create a feedstock. Injection molding: the feedstock is injected into a mold, where it takes the desired shape. Debinding: the binder is removed from the molded part, often using heat or solvents. Sintering: the remaining metal powder is heated to a high temperature, causing the particles to bond together and form a solid part. Advantages of MEM. Complex shapes: MEM can produce parts with complex geometries that are difficult or impossible to create using other metalworking processes. High precision: MEM can achieve tight tolerances and produce parts with very fine details. Cost effective: MEM can be less expensive than alternative manufacturing methods, especially for high-volume production. Material versatility: a wide range of metals can be used in MEM, including ferrous metals, hard metals, and special metals. High production rates: MEM is a fast process compared to some other metalworking techniques. Applications of MEM. MEM is used in a variety of industries, including medical implants, surgical instruments, and diagnostic equipment. Consumer electronics, cell phones, wearable devices, and other electronic components. Automotive, rocker arms, turbocharger vanes, and other automotive parts. Aerospace, various components where strength, precision, and lightweight design are important. General industrial, gears, bearings, and other mechanical components. Limitations of MEM. Start-up costs: the initial investment in specialized equipment can be significant. Tooling lead times: the time required to design and fabricate the molds can be relatively long. Design change costs: modifying the part design after tooling is created can be expensive. Metal injection molding, MEM, and powder metallurgy, PM, are both metalworking processes that utilize metal powder, but they differ significantly in their manufacturing approaches and capabilities. MEM involves mixing metal powder with a binder, forming a feedstock that's injected into a mold, while PM uses powder to form parts through compaction and sintering. MEM is favored for complex geometries and high-precision parts, while PM excels in larger, simpler parts and cost-effectiveness for some applications. Key differences. Feedstock preparation. MEM utilizes a feedstock where metal powder is mixed with a binder, creating a material that can be injected into a mold. PM, on the other hand, uses raw metal powder directly, which is then compacted and sintered. Manufacturing process. MEM employs injection molding techniques, allowing for complex shapes and high-precision parts. PM relies on compaction and sintering to create parts from powder. Shape and size. MEM is particularly well suited for producing intricate and small to medium-sized parts, while PM can handle larger and simpler shapes. Cost. MEM can be more expensive than PM due to the specialized feedstock and molding processes, especially for low-volume production. Density. MEM parts generally achieve higher density and better physical properties due to the controlled powder flow and uniform friction in the injection molding process. Material limitations. MEM is often used for materials with high melting points like stainless steel and tool steels, while PM can be used for a wider range of materials. MEM advantages. Complex geometries. MEM's ability to produce intricate shapes with fine details and thin walls makes it ideal for applications requiring complex designs. High precision. MEM parts can achieve high levels of dimensional accuracy and surface finish. Cost effective for high volumes. MEM can be cost-effective for high-volume production of small to medium-sized parts. PM advantages. Cost-effective for simple shapes, PM is often more cost-effective for simple, large, or high-volume parts. Wider range of materials, PM can be used for a broader range of materials compared to MEM. Net shape parts, PM can produce parts with close to final shape, reducing the need for extensive machining. Metal injection molding vs die casting, in-depth comparison. In essence, MEM is the preferred choice for complex, high-precision parts, while PM is more suitable for simpler, larger parts and cost-effective solutions. The best choice depends on the specific application requirements, part complexity, desired precision, material selection, and production volume. Metal injection molding, MEM, and die casting are both metalworking processes used to produce parts, but they differ significantly in materials, process, and resulting part characteristics. MEM uses powdered metal feedstock, while die casting uses molten metal. Here's a more detailed comparison. Materials. Typically uses nonferrous metals like aluminum, zinc, magnesium, and copper alloys. Uses a wider range of metals, including stainless steels, titanium, nickel, tungsten, and copper, as well as various alloys. Process. Involves injecting molten metal under high pressure into a die mold. The mold is typically made of hardened steel. Mixes metal powder with a binder to create a feedstock, which is then shaped into the desired form and sintered, heated to remove the binder and solidify the metal. Results. Produces larger, less intricate parts in high volumes, often with tight tolerances and good surface finishes. Specializes in producing complex, intricate, and small parts with tight tolerances and thin walls. Key differences summary. Feature. Die casting. Metal injection molding. Material. Die casting nonferrous metals, aluminum, zinc, etc. Metal injection molding ferrous and nonferrous metals, including MEM alloys. Process. Die casting inject molten metal into a mold. Metal injection molding mold and sinter powdered metal feedstock. Typical parts. Die casting larger, less intricate, high volume. Metal injection molding complex, intricate, small, and thin-walled. Process steps. Die casting melting, injection, cooling, ejection. Metal injection powder mixing, molding, binder burnout, sintering. Mold. Die casting typically made of hardened steel. Metal injection specialized tooling for molding and sintering. Material selection. Die casting depends on alloy composition and properties. Metal injection alloy composition and properties. Die casting and powder metallurgy, PM, are distinct manufacturing processes that create metal parts from molds. Die casting uses molten metal poured into a die, while PM uses compacted metal powder. Die casting offers high production rates, complex shapes, and net shape parts, but tooling costs can be high. PM offers lower tooling costs, flexibility in material choices, and potentially harder, tougher components, but may have limitations in geometry and net shape capabilities. Die casting. Process. Molten metal, typically nonferrous alloys like aluminum, magnesium, or zinc, is injected into a mold, die, under high pressure. Advantages. High production rates, complex shapes, and net shape parts, meaning the part requires minimal post-processing. Disadvantages. High tooling costs, potential for defects like porosity, and limitations in material choices. Applications. Automotive parts, gears, pistons, aerospace components, lightweight structures. Powder metallurgy, PM. Process. Metal powder is compacted and then heated to create a solid part. Advantages. Lower tooling costs, flexibility in material choices, can use both ferrous and non-ferrous metals, and potentially harder, tougher components. Disadvantages. Limitations in geometry, may require post-processing, and can be heavier than die-cast parts. Applications. Bearings, gears, engine components, and parts for high-temperature applications. Key differences. Feature. Die casting. Powder metallurgy, PM. Process. Die casting molten metal injection. Powder metallurgy powder compaction and sintering. Materials. Die casting primarily non-ferrous alloys. Materials powder metallurgy ferrous and non-ferrous metals. Tooling costs. Die casting high tooling costs. Powder metallurgy lower tooling costs. Production rate. Die casting production rate high. Powder metallurgy slower. Net shape. Die casting yes, often net shape. Powder metallurgy net shape limited. Complexity. Die casting high complexity. Powder metallurgy limited complexity. Material properties. Die casting generally lower strength toughness. Powder metallurgy material properties can be harder tougher than die-cast parts. Porosity. Die casting potential for porosity, defects. Powder metallurgy controlled porosity possible. Choosing between die casting and PM. The choice between die casting and PM depends on the specific requirements of the application. Consider factors like production volume, part complexity, material properties, tooling costs, and net shape requirements. Investment casting and metal injection molding, MIM, are both precision manufacturing processes used to create complex metal parts, but they differ significantly in material capabilities, production volume, and part complexity. MIM excels at high-volume production of intricate, small parts, while investment casting is more suitable for smaller production runs of larger, more complex parts, especially when using a wider variety of materials. Key differences. Material compatibility. MIM is primarily used for high melting point metals, while investment casting can handle a broader range of materials, including those with lower melting points. Production volume. MIM is best suited for high-volume production of small parts, while investment casting can handle smaller production runs and larger parts. Part complexity. MIM is excellent for creating highly intricate geometries and net-shape parts, often requiring minimal post-machining. Investment casting can also produce complex parts, but may require more machining to achieve desired tolerances or features. Cost. MIM can be more cost-effective for high-volume production, while investment casting may be more suitable for smaller batches due to lower upfront tooling costs. Size and weight. MIM is best for small, lightweight parts, under 20 grams, while investment casting can produce parts weighing up to 3 kilograms or more. Surface finish. MIM generally achieves a superior surface finish compared to investment casting. In summary, MIM high-volume production, small, intricate parts, high melting point alloys, net-shape parts. Investment casting smaller production runs, larger parts, wider material range, potentially more post-machining. The MIM, metal injection molding, process involves 4 main steps: compounding, injection molding, debinding, and sintering. These steps work together to produce complex, high-precision metal components. 1. Compounding. Fine metal powders are mixed with a binder, typically polymers and waxes, to create a feedstock. This feedstock is then granulated into pellets for use in the injection molding process. 2. Injection molding. The feedstock pellets are melted and injected into a mold cavity under high pressure, forming the green part. This process allows for the creation of complex geometries and thin walls. 3. Debinding. The binder is removed from the molded green part in a controlled process. This can be done through solvent debinding, thermal debinding, or a combination of both. For sintering, the debound part, known as the brown part, is heated to a high temperature, near the metal's melting point, in a protective environment. This process causes the metal powder particles to bond together, forming a solid, dense component.
Metal injection molding is a manufacturing technology that utilizes metal powders combined with organic binders, using injection molding technology to produce highly complex structural metal components. Parts are subsequently processed and sintered to yield high-strength, intricately shaped parts. Components produced by metal injection molding are used by medical and dental markets, general industrial markets, firearms, automotive, electronics, miscellaneous other users, aerospace, and automotive. We see here that medical, dental, and general industrial and firearms are the dominant users of metal injection molded components. So one of the questions we ask is my part a good fit for MIM? And here we see in this model material performance, component cost, production quantity, and shape complexity. The closer we can get to the intersection of these four circles, the better the application is for metal injection molding. Powders used in the metal injection molding process are produced from gas atomization. Here we see a model of the gas atomization process. We start with molten metal. Material is then poured into a holding chamber, and from the holding chamber, it is discharged into the atomization area, where the molten metal is hit with high pressure gas, inert gas, to produce metal powders. It is then subsequently processed and finished for use. And you can see the spherical nature of the gas atomized powders. This is ideal for metal injection molding because they have a low coefficient of interparticle friction. Metal injection molding process starts with metal powder and binders. Those binders are then compounded into a paste-like material, which is turned into small pellets. This becomes the feedstock that is used in the metal injection molding process. Components are molded in a metal injection molding press. From there, the binders are removed in what we call a debinding process or dewaxing. After the debinding process, the components are sintered at elevated temperatures, typically in the 2350 degrees F or higher, in a protective environment, or in some cases in a vacuum. And then post-sintering processes are performed as necessary. The gas atomized powder that's used in metal injection molding is put into the feedstock granules, as you can see on the right. The feedstock is then fed into the molding press, where the components are molded under high pressure. After molding, the binder is removed through the debinding process. The typical binders of polyoxymethylene or POM, polyethylene or polypropylene, which are synthetic or natural waxes, and stearic acids are also used as binders. There's a catalytic debinding process, which is an acidic gaseous atmosphere that's used to remove the POM binders as well. We can also use thermal or solvent debinding using acetone, heptane, or an aqueous solution. After debinding, components are then sintered either in a pusher type continuous sintering furnace or in a batch type sintering furnace at elevated temperatures, either in vacuum or protective atmosphere. As you can see, in metal injection molded components, we oftentimes see as much as 15 to 20% shrinkage after the sintering process. Some common MIM applications are firearms. Here we see an example of some MIM components that were used in a Smith & Wesson rifle. This is an example of a sound tube that's used in a hearing aid made from 316 stainless steel. And we see the orthodontic appliances using a metal injection molded 17.4 pH stainless steel. Metal injection molding produces intricate components used by medical, electronics, recreation, and other industries. MIM Technologies offers outstanding value for parts requiring intricate geometry and superior material properties.
Can I use conventional injection molding machines as metal injection molding machines? No, a conventional injection molding machine cannot be directly used as a metal injection molding (MEM) machine. While both processes use injection molding, MEM requires specialized equipment and a different approach due to the unique characteristics of metal powders and the high temperatures involved. High temperatures and pressures. Metal injection molding involves heating and injecting a mixture of metal powder and a binder, which necessitates much higher temperatures and pressures than plastic injection molding. Material compatibility. Traditional injection molding machines are designed for plastics, and their components are not designed to withstand the extreme heat and wear associated with metal processing. Plunger and cylinder design. Plungers and cylinders in MEM machines must be designed to handle the high pressures and temperatures without galling or malfunction, which is a significant challenge with conventional machine designs. Debinding and sintering. MEM parts require additional post-processing steps like debinding, removing the binder, and sintering, heating the parts to fuse the metal powder. These steps are not part of conventional injection molding. Specialized equipment. MEM machines are designed with features that are not found in conventional machines, such as specialized injection nozzles, heat control systems, and tooling designed for metal powders. Thank you for your time. My name is Amar Janina and please watch my other mold design videos.